Well, thank you for a very kind introduction from Professor Yakub. And my talks will be mainly focusing on tissue engineering and especially on the scaffolds works. So, in application for the heart failure. Thank you. So, my talks will start with a bit of an introduction about tissue engineering and especially for cardiac applications, and what are the applications in the heart failure and especially myocardial infarctions. Um, uh, well, our audience probably more experienced than I do on the current treatments, so I might skip some of those. And what are the tissue engineering strategies for treating myocardial infarctions? And what are the design criteria for making the scaffolds for the applications? And what are the current scaffold types currently employed in tissue engineering? And some of our ongoing research in QCRCs. So in terms of tissue engineering, central of tissue engineering, we have the scaffolds, which are the three-dimensional matrix that acting as a temporary support for growing cells and with the nutrients. And follow on with the scaffolds, we can put into a bioreactor system to give appropriate electrical, physical, mechanical, and chemical stimulations, and followed by implantations of tissue engineering construct. And that's one of our classical approach in tissue engineering. With the new approach, we are looking at the intelligent scaffolds where with the accelerator approach, so we design the scaffold to have appropriate biochemical signals and actually also physical cues as well. Then we implant direct into humans, and we using human essentially as the bioreactors, and through human we do cell recruitment and getting nutrients and all the mechanical, biomechanical, biochemical stimuli from human directly. So one of the main consideration in the tissue, as I mentioned, is the scaffolds, and this supports in terms of mechanical, physical, and biological cues. And cells, as we heard from our previous talks from Pfizer and Professor Yakub, there are various types of stem cells, and actually Dr. Miller. So the stem cells, autologous or progenitors or iPS, and these are considered as appropriate cell source, or we have to decide which one we want to use. And obviously the scaffold performance, both at the cellular or tissue level is important, so we have to make sure these scaffolds support all the viabilities, proliferations, and also function such as support for cardiac functions and mechanical function in terms of the valves. One important aspect in tissue engineering is also regulations. And this regulations has been quite a hindrance to tissue engineering development, where safety and the clinical trial on tissue engineering is very limited, and most of it is in compassionate use. So, as we know, myocardial infarctions generally cause fibrotic collagenous rigid tissues, and this affect the function of cardiac functions. So we all know this, I'll skip this. And the current treatments, as Dr. Miller has mentioned in the previous talk, use LVAD, and in very severe cases, heart transplantations. And similar to tissue engineering, we aim to restore or repair the left ventricular functions. So what are the current tissue engineering strategies? We have the use of a cardiac patch or full graft, and or use of injectable biomaterials. And these are mainly with three applications in mind, is you can add as a supporting materials directly with the direct use of the scaffold or the biomaterials. Or you can use as a cell delivery vehicles. You can deliver stem cells, cardiomyocytes, and depends on the choices. Or you can use as a biomolecule delivery vehicles. So it could be mRNAs, as mentioned by Despina yesterday, gene therapies, and or growth factors, etc. So with this application in mind, what are the criteria we need to think about when making the scaffolds? We have the thinking about biocompatibility and biodegradabilities. Excuse me. And these are important where the polymers or Like in plants has to be non-toxic, non-immunogenic, and in relation with the degradations, its degradation product has to be non-toxic as well. And in addition to the polymer property itself, we also need to think about mechanical support. When human myocardians, we have stiffness between 20 kilopascals to 500 kilopascals. And if you are thinking as a cardiac patches for example, molecular delivery vehicles, we need to have some stiffness. So generally, we can consider 20 kilopascal to make sure the patches stays there. And if you have application in mice where you're using as a reinforcement material for myocardial walls, you need to consider what are the stiffness you need to actually support the wall to reduce the wall stress. And in terms of hydrogel application where injectable biomaterials, you need to consider things like the gels has able to go through the needles you use for injections, and what are the polymerization time from the solution to gels that has to be timing right so that you can actually inject the materials, but at the same time it has to polymerize in time so it doesn't get washed out. In terms of using graft or cardiac patches, you have important criteria as the thickness. So if you are to consider, for example, a full graft, generally we're talking about 10 millimeter thickness. And cardiac tissues are very high cell densities and has a very high metabolic rate. So you will run into what we call diffusion constraint, where the oxygen and nutrient diffusions are limited. So one of the strategies people are consider is taking care of the porosity and vascularization, where you introduce channels, essentially like our blood vessels, to actually enhance the cell penetration and colonizations into a full graft. And especially for cardiac tissue engineering, one important aspect is thinking about electrical impulse propagation rate. So we know that the cardiac tissues have taken electrical signals, so we need to consider this as part of the design criteria. So with this in mind, let's look into the 4 common scaffold types that are currently used in tissue engineering. These are hydrogels, decellularized scaffolds, biological scaffold, and synthetic scaffolds. The hydrogels generally are polymerizable polymers made from either collagen, chitosan, polyethylene glycan, or fibrin gels. And this, you can have clear solutions and then generally polymerize into something solid. And this mainly act as a temporary matrix for cells or biomolecular deliveries. And you could also add a myocardial wall reinforcement where some of the gels actually can be designed to have a very good stretch, stiffness, and mechanical properties. And the second type of scaffolds I'm going to introduce will be decellularized scaffolds. And these are scaffolds taken from a whole organ or tissues, and then we remove the cells by detergents. And you can see in this heart where there's a protocol where people decellularize the whole heart over 7-day periods, where you can see the red where the cells are being removed, and you're left with essentially like a collagenous bag of tissues. But within that is a very good ECM architecture and all the blood vessel structures that circumvent some of the thickness problems and also provide all the right matrix for it. And in application-wise, people will think the use of recellularization for classical approach, or you can have direct implantations to involve recruitments. And third type of scaffolds I'm going to be discussing about is the biological scaffolds. So biological scaffolds are material that is biological in origins. So these are collagen, alginate, fibrins, and etc. And they have advantage where it has natural adhesion cell size, and its degradation pathways actually exist in most of cells already. So it's often used to blend with other synthetic polymers which lacks a natural adhesion size and can be incorporated with other biological molecules as well. So one interesting type of natural biological scaffolds is the use of cell sheets, which I believe is also in our previous seminars, where they grow cells on a thermally responsive polymers. And the cells will become conference and produce extracellular matrix. And by the special property of this type of polymers, when you change the temperatures, it actually becomes hydrophobic to hydrophilic, which allows the cell to detach. And this, you can see a detached cell sheet like floating in PBS solutions. So essentially, you have a sheet of cells with the extracellular matrix intact. And this has a potential application where we can use for transplantation to injured hearts, and by introducing the right cells, we might be introducing a right paracrine effect as well. And it's also possible to stack the cell sheets for multi-layer constructs. Of course, there are problems with the mechanical properties in this aspect. And the last type of scaffold I will introduce is synthetic-based scaffolds. And these are scaffolds made of synthetic biomaterials, which are, for example, polycarbolactone, polylactic acid, PEG and PBA, for example. And they have an advantage where it's actually fairly easier to process, and lots of existing processing methods exist. And you can tailor its biomechanical profile or biochemical profile by using either porous nanofibers, or by introducing different physical properties, chemical properties, or by introducing molecular biological signals into the scaffolds as well. And there are different type of foams where you have gels, fibrous. You can do soil-free fabrications, or you can make a porous scaffold like this type. And general synthetic scaffold lack of biomimetic surface, but so we usually cooperate with some sort of biological molecules. And one type of synthetic scaffolds or synthetic polymers are interesting in cardiac tissue engineering, and especially in neural tissue engineering as well, is use of conductive polymers. And these are special type of polymers with loose pi electron systems where they act like a metal, so it actually provide conductivities. And so you can use this polymer directly, or another approach is actually taking existing biopolymer that we use, such as ketosans and silk, in one of the reports, that you can coat it with something electrical conductive, so such as carbons, and this actually provides similar properties as well. So this is a quick summary about all different advantage and disadvantage of using different type of scaffold. It really depends on the applications of the materials. So, such as hydrogels, you can use because it's easier to administrate. You can avoid open heart surgeries. But the problem is you have the generation times and potential washout you have to be considered. And geometry of hydrogel is generally more difficult. Decelerated scaffold is really good because it actually maintains ECM structure and vasculature. But the complication in the deceleration process generally affect the ECM integrities. And maybe there's some incomplete wash as well, so you may get cell debris, which some people believe it causes inflammatory responses or lead to calcification as well. And biological scaffolds, which are generally very good in biomimetic surface, and there's no cell exist. But problem with poor mechanical properties are often associated with this type of polymers. Synthetic scaffolds, on the other hand, is very easy to produce, and you can tailor the architectural and mechanical properties, for example. But the degradation products are always a concern as well. And there are in some in vivo study where thickening and fragmentation of the polymer actually cause some problems. So what are the ongoing research in QCRC, especially in tissue engineering field? One of our previous studies is looking at maturing iPSC cardiomyocytes. So as Professor Yakub mentioned, we're using physical cues to promote maturation of the immature cardiomyocytes. Through lithographies, we actually make a mold with lots of grooves about 10 micrometers apart. And we cast with PDMS and use PDMS as a material for our scaffolds. And this allows, sorry, I forgot to say, then we coat with fibronectin to allow cell adhesions. This allows the cells actually adhere with the groove and align with the groove. So by providing alignment facilities, we actually promote the immature type of cardiomyocyte to show cell alignment, organize sarcomeres, and even improve some calcium signaling properties. So through physical cues, we can actually promote iPSC cardiomyocyte maturations. So ongoing research is actually moving to using polycarbolactone fibers which are also aligned. And we do this through a jet spraying techniques where we spray the polymer of PCL in air guns at a very fast rotating speed of the drums. This actually provides alignment. As you can see, we increase the speed of the drum, we increase the alignments. And this is the actual thick scaffold, so you can see in here. And we introduce both the alignment, allow the cell to align with it, and also change the mechanical property into anisotropy properties as well. And one of ongoing research as well is modification of the PCL itself. So we can either modify the surface with the biomimetic molecules, or we can incorporate interesting molecules, drugs into some sort of drug-related devices that we can incorporate into the scaffold as well, and then provide a long-term and local release of the drugs or growth factor proteins. So in conclusions, the designer scaffold has very versatile potential for heart failure treatments, and there are several strategies that have been developed in tissue engineering. All strategies are being considered. They all have its advantages and disadvantages. So this is a lot of ongoing research focused on this. And in QCRC, we mainly focusing on designing functionalized PCL scaffolds and in applications for treatments. And last slide, lung treatments, thanks to Professor Yakub and our tissue engineering team in QCRC and our team in London in Mike Yakub Institute. Thank you.